All right, welcome to the section 3.1 recap. What do you need to know? First of all, you need to know the definition of a derivative. Derivative is a slope at a point. We can find it two different ways. We can take the limit as h goes to 0 of the function at some value of h just to the right of x, minus the value of the function at x divided by the x value between the 2 points. It's a slope, change in y over change in x. We can also do it slightly differently. At some point x equals a, the derivative at that point equals the limit as x goes to a, as x approaches a, of f of x minus f of a divided by x minus a. Of course, x minus a is the same as h because a is getting closer and closer, well, x is getting closer and closer and closer to that point, and f of x minus f of a is the same as f of x plus h minus f of x. Sometimes the second one is just easier to simplify than the first one in a complicated case. Notation, what do you need to know? You need to know f prime, you need to know y prime, you need to know derivative of f with respect to x, derivative of y with respect to x, the derivative with respect to x of the function. They are all exactly the same thing written in multiple different ways. Graphs, f to f prime. If we are given the graph of a function, we can find the slope at various points and then plot those points. Plot and curve fit. What about if we're given the derivative graph? We just sketch tangent lines. If we know that the derivative is equal to 6, we draw a tangent line with a slope of 6. Then we move over and it's equal to 2. We draw a tangent line with a slope of 2. And we just keep doing that until we get all these tangent lines. And then we just curve fit over the tangent lines at each point. Table. What if we've got a table of data? Well, we find average slopes between points. And we generally just go say, well, halfway between each point. So points at 0, 5, we find the average slope from 0 to 5, and we say that that will be at 2.5. We're ballparking. It's a rough approximation, but it generally works. And finally, cramming in, we've got one-sided derivatives, and this is on a closed interval. We can find a one-sided derivative at the end of a closed interval. And of course, we also need to understand that the derivative at the point may not exist. The only way it can exist is if they are the same on both sides. And we saw an example of that back in the last video. All right, guys, that's section 3.1. Please get a hold of me if you have any questions. And we'll start getting ready for the quiz.